Hello, everyone. Good morning, everyone.
Morning.
Hey, sir.
If you're all ready for another exciting day of learning physics.
Of course, as always.
Yes, sir.
It's our life. It's what we live for, right?
I was actually wondering, I shot you a message on Monday.
Okay.
I didn't hear back from you. It was
Let's see.
concerning the lab.
It was
It's
regarding the lab.
Yeah, it's wyounger@tcc.edu, right?
Yeah.
Okay.
Let's see. Let me see.
Yeah. It was just asking about the first couple of questions on the lab, because the question asks show that, you know, this function is this.
Right.
But all of that information is basically given earlier on that lab document. Yeah. So I was wondering if that question was pretty much a given.
Yeah, it's pretty much you just do try to close your book and do it on your own, or close the worksheet and do it on your own. It's just going through the calculus, which is really trivial on the first three. It's a little bit more work on the last three. I did find your email, by the way.
Okay. Honestly, I couldn't really I couldn't follow what it was saying, because I think it's because I'm not following exactly what those symbols mean.
Gotcha. Okay. Let me answer that then real quick. I'll turn on my document cam and give you an idea of that, and it'll probably help everybody. You got to like what, 1 or 1:30 today to turn it in, or is that next week?
Yeah, I don't know the
submission is set until 12 o'clock tonight.
Okay.
Yeah, I was gonna say the Canvas link says midnight, but you usually say before the beginning of the following lab.
It's supposed to be the beginning of lab, and it by default does 11:59, and actually sometimes I change it, and if I don't hit the exact right button, then it'll turn it back to 11:59. So that's probably what happened, but I'll give you guys till midnight, so don't worry about that. The big deal is there is an uncertainty in a measurement. So if you have a measurement X, it should be either X bar or X bracket should be the first thing. They should have a plus or minus, then a sigma sub X. That's your uncertainty. Now that can be the what I call the standard error, not the standard deviation, but the standard error. Or it can be the instrumental uncertainty. Whichever is largest, it's got to be that. But no matter what, that's the symbol that's given it, whether you got it from calculating the standard error, or whether you got it from using the instrumental error, or whether you got it from a calculation of propagation of error. That's always what that value is. Okay.
Okay, and X bar, that's the average value?
Yeah, that's the mean or the weighted average in some weird cases where you happen to have weighted average, but generally it's just the mean or the average. Yep. There's another symbol we use, and that's sigma X over X. And the way you calculate that is you take this sigma X and you divide it by this value. And that's called the fractional error. Okay. So that's another symbol that you have to use. Again, this might be the standard error, but it could be the instrumental error, or it could be an error you get from a propagation of error formula. Okay. Now the propagation of error formula, if it's a function of one variable, sigma f is just the absolute value of df over dx times the uncertainty in x. But if it's a function of many variables, then the uncertainty in f of x, y, ... is equal to partial of f with respect to x squared sigma x squared plus partial f with respect to y squared sigma y squared plus ... for as many variables as the function has.
And that's kind of unfortunate. Your stream actually looked really good until it became
Just went to
shitty just
crap.
a second ago. Yeah.
Let's do that. Can you see that better now?
Well, yeah. What is the sigma f again?
The sigma f would be the uncertainty in some function. So for instance, let me give you as an idea. I got to click somebody else in real quick. As an idea, v of x, y, z could be a volume as a function of width, height, and depth. So it would be literally x times y times z. So that's an example of f of x. So you've got an x that has a expectation or a best estimate plus or minus an error. You've got a y that's specified the same way, and you got a z that's specified the same way. What do you do to calculate the volume? Well, you take the best x, the best y, and the best z, and you multiply them, and that'll give you your best estimate of the volume. Then what is the uncertainty? Because you're supposed to be able to report v as v bar plus or minus sigma v. Well, that's what sigma v is. That propagation of error formula.
Can I jump in real quick?
Yes.
So I think one of the things that's kind of confusing to me and maybe a few other people is that you are asking for partial derivatives, which we have not been taught yet in Calc 2, if anyone else is in the same Calc 2 class as I am.
Yeah, you normally don't get to them until Calc 3.
But 4, 5, and 6 all require the partial derivatives. And in your YouTube video, you only give us the partial derivatives for number 4, but we are not given the partial derivatives that are needed to solve 5 and 6.
Well, that's why in the video where I taught you this, I showed you how to do a partial derivative. Basically, a partial derivative is the same as a regular derivative. It's just you're pretending like the other variables, like in this case, you're pretending like y and z are constants. So if this was x times 2 times 3, the derivative of this with respect to x would just be 2 times 3. And you can literally do it like that. You can say partial of f with respect to x is equal to, well, let's do it this way. Hold on. I'll take an extra step to make sure everybody follows what I'm saying here. So I'm going to say it's the derivative with respect to x of x times 2 times 3. Only never, ever, ever act on those 2 and 3s. So would you know how to do the derivative of 2 times 3 times x? But you're absolutely right, Kevin. Yeah, y'all aren't taught that. But that's also the way it happens in engineering and science. You normally learn your math from your science instructor or your engineering instructor. So if you had 2 times 3, which would generally be 6x, what would be the derivative of 6x with respect to x? Anyone?
6.
Yeah, so we're just going to write 2 times 3. That's what I mean by don't combine these. Don't do that multiplication because you can't multiply y times z. You don't know what that is. So now you can say the partial of f with respect to x is actually equal to y times z. Similarly, if you had f of x, y, whatever, is equal to 2x squared plus 3xy plus 4z cubed xy, and you want to take the partial of f with respect to x, well, this first term is easy enough. That's just the regular derivative, so you're going to get 4x. This next term is actually pretty easy too. Remember, if you remember that y is supposed to be like 2. So this is just linear, so I do 3 times y. And then this one, of course, is the same way. It's linear in x, so it's just 4z cubed y. So yeah, that is an actual problem that we're well aware of. We know that you don't necessarily know partial derivatives, but they're so patently obvious that we expect you to be able to learn them from this brief little intro. Now, if you take the partial of this with respect to y, there's no y term in there, so that's 0. There's a linear term in y here, so that's just 3x. And there's a linear y here, so that's just 4z cubed x. And then finally, the partial of f with respect to z. There's no z there, there's no z there, so those are both zeros. And there is a z here. In fact, it has to become 3z squared, so that's going to be 12z squared times x times y. So that's what I was standing on, is you guys being able to do the partial derivative yourself. So for instance, in this case, we already did the partial of v with respect to x is just yz. The partial of v with respect to y, that's just going to be xz. And the partial of v with respect to z, actually with respect to z, is just going to be xy. So if you want to know the uncertainty in v, you're going to take yz, square it and multiply it by sigma x squared. You're going to take xz, square it, multiply it by sigma y squared, and you're going to take xy, square it, multiply by sigma z squared, and then take the square root of everything. Now, believe it or not, that's actually fine. And what this formula really means is, since you have x is equal to some x bar plus or minus sigma x, and you've got some y is equal to y bar plus or minus sigma y, and you've got z is equal to z bar plus or minus sigma z, they mean put in y bar, z bar, x bar, z bar, x bar, y bar in there. And of course, these sigmas are what go here and here and here. Does that help you, Cadmium and Gavin?
Yes, sir.
Yeah.
It's a little intimidating the first couple times you see it, and that's okay. You should be intimidated a lot in your science and engineering fields. That's sort of the mark of learning new stuff, right? Now all you got to do is, I asked you, for instance, to do x plus y. Let's do something different. Let's do f equals 3x plus 4y. Okay. So that's, this could be, for instance, like the perimeter of a fence, and you've measured x and y really well, right? So you've got some x values equal to x bar plus or minus sigma x, and you've got some y is equal to y bar plus or minus sigma y. And now you have to use those variables that you measured and have uncertainties with, and determine not only the function 3x plus 4y, but you also need to find out what the error is. So we need f equals question mark, and we need sigma f is equal to question mark. So what you're going to do is you're going to take the partial of f with respect to x, which you can see is just 3, and you take the partial of f with respect to y, which you can see is just 4. And then you're going to plug into the formula that we used before, which is that one that, of course, let me focus this at this angle, which of course has disappeared and started getting ugly when I wrote it. But that means the uncertainty in any function of any number of variables is equal to the square root of the sum of the squares of the product of the derivative of the function times its uncertainty in that particular variable. So the x down here matches the x here, the y down here matches the y down here, and for however many variables you have. Now that's just the uncertainty. So that's the thing that goes after the plus or minus when you do the actual calculation. So the actual sigma f in this case is going to be, I'm going to take the partial derivative of f with respect to x, I'm going to square it. So I'm going to write 9 sigma x squared. And then I'm going to square this one and write 16 sigma y squared. And that's actually fine. I can actually submit that now. I can say this is the actual uncertainty in f. Well, you might say, well, what's f? Well, f is actually going to be equal to 3 times x bar plus 4 times y bar. So that's sort of your best estimate of F is using your best estimate of X and your best estimate of Y and whatever variables are there, that would give you the actual function. But you need to be able to report this as F is equal to some F bar plus or minus sigma F. And this is what allows us to do the sigma F. Now, I might actually be able to make something nice out of this by doing sigma F over F. In fact, it doesn't work out so well because it's a binomial term. So if I square this, there's not really a lot of simplifications that come out. So we're just going to leave it as that. So really what I do is if X, let's say X was equal to 1.96 plus or minus 0.02, and let's say Y was equal to 3.79 plus or minus 0.03. If that was the case, then what I would report is F is equal to, so this is going to be my F bar. I'm going to write 3 times 1.96. And by the way, let's say these units are centimeters. So I had to put parentheses around it since I put it on the outside. 3.196 centimeters plus 4 times 3.79 centimeters. When I do this actual calculation, I get 3 times 1.96 plus 4 times 3.79, and I get 21.04 centimeters. Now, I don't know where to round that to. I don't know that until I figure out what the sigma F is. Well, now let's calculate that sigma F. Well, according to the formula, sigma F is going to be equal to the square root of 9 times sigma X squared, so that's 0.02 centimeters squared, plus what was it, 16 times 0.03 centimeters squared, square root. So I now take that, I'm going to do 9 times 0.02 squared, and I'm going to say plus 16 times 0.03 squared, and that'll give me the square root of 0.018 0 centimeters squared. So now I take the square root of that, and I get 0.1341 centimeters. Okay. Well, the rule is we normally round this to exactly 1 sig fig, unless it's 1 followed by 4, 5, 6, 7, or 8. And then we might choose to do 2. I'm never going to take off for you choosing either way. Okay. So for right now, what I'm going to say is I can now report F to be 21.0 plus or minus 0.1 centimeter. And the reason why I round it there is if I'm uncertain by 1 in the 10ths place, I have no hope whatsoever of knowing what the 100ths place is. So why would I report the 4 up here? So that is how this process is done. So the part after the plus or minus, the sigma has to be the standard error which is the standard deviation by the square root of n divided by the square root of n, or the instrumental error, you got to choose the largest, or it's got to be the propagated error. Which is that formula that we use, the sigma F is equal to, partial F with respect to X squared, sigma X squared, plus partial F with respect to Y squared, sigma Y squared, ... and then take the square root of all that. Does that help you, Gavin? Or did everybody
Uh,
leave on a mutiny?
Yeah, yeah.
So yeah, I did a lot of these. In fact, you can see in the video that I made for you guys, you can see me actually doing calculations like these. So I'm sort of showing you exactly how to do it. And I just want you to be able to do it on your own. So it's a lot of them are just me more or less doing the exact same thing. I mean, this is actually harder than the one that I gave you because I gave you x plus y and x minus y. Didn't even have the 3, didn't even have the 4, right? So all you have to put in instead of 3 squared and 4 squared is just 1 and 1 squared and -1 squared, or 1 squared and +1 squared. So that's really what it's trying to do, and that's basically called a derivation when you're working out one formula to get another formula. So that's what that sheet's about, and it is the way you're actually supposed to handle errors. I mean, this is, if you're taking this course at UNC Chapel Hill or Virginia Tech or UVA, and hopefully just about every place that offers a 4-year degree, you should be doing this kind of error propagation instead of sig figs. The algebra-based course, I could make an argument for not doing it there because obviously most people don't have algebra, but we did it at Chapel Hill for the algebra-based course because we looked at our enrollment every semester and all of them had finished calculus. So we went ahead and did it this way for the algebra-based course too, which is really, kind of cruel, but I liked it. So any other questions on that?
What was the propagated error again?
The propagated error is the thing that comes from
that one up at the top.
Yeah, it's the one that either comes from this formula when the function has only one variable, or this formula.
Gotcha. Thank you.
No problem. So yeah, whenever you have to use a formula to compute something, there's no way of going through and doing standard deviations and stuff like that, because you're just taking an x, a y, and you're doing a calculation of f. So you only get one f. There's no way you can do anything but do a propagation of error. So that's how that works. All right.
Sir, speaking about formulas, I have a question for the exam that's next week.
Yeah.
When will you be releasing the formula sheet of the given formulas?
I don't make a formula sheet for you guys. You make your own, and then you show it front and back to the camera when you're doing the respondus midterm.
So we are allowed to write down all of our own formulas?
Yes, but that's why you have to show them to me, because you're only allowed, with the exceptions of the ones that I explicitly told you, you're only allowed the ones that are labeled with like 7-11 or 6-4 or something like that in your textbook.
Okay, will you be telling us the 7-11s, the list of those that we can have?
No, you can just look in your book and you'll see them. That's why I've sort of been boxing them off as the semester progresses and saying, this is a formula that's in your book, and it's labeled so you can use it. So I've been saying that throughout the semester. But yeah, the bigger thing is just, open your textbook, look in chapter 1, write down all those equations. I suspect a lot of them be stuck in your memory already, so you won't even have to do that. The other thing is you're also allowed any of the constants, any of the prefixes for the SI system, any of the integral formulas that you see in the front and inside back cover of your textbook. So you can, make copies of those if you want, or you can just copy down the constants that you might want or whatever. But yeah, I never do that. In fact, the publishers tried to be nice and give us the equations, but when they turn them over, they're never in the proper format, so they get mangled. And I've tried to make some myself, and I've spent literally on one sheet one time, I spent about 6 hours typing them all up, and then the next time I opened them, they were damaged again, so I just gave up. Okay.
Thank you, sir.
No problem. But yeah, everybody is allowed an equation sheet, so make sure you all remember that. Make sure you bring it with you. You're allowed, you need to have your own scientific calculator. You cannot use your cell phone as your scientific calculator. Okay, you need to have a separate one. If you got this special issue, like a lot of people I get are from the Navy and they'll be on call on a day of a test, so they are not allowed to leave their phone without them, away from them at any time. You just let me know that in advance, and then when the test is going on, if you actually have to take it, you're going to have to, you know, show me the number that's calling or whatever like that, and then have the conversation, if you can, in the public setting, so I can tell it's not about, you know, math or science or whatever. That recording does not go out to anyone. It's monitored by people looking for suspicious behavior. But generally speaking, I doubt you'll have a phone call during it. If so, I can always make up another test and let you redo it. Anything else before we get jamming on this stuff? Okay, so last time we were in chapter 7, which is on work and energy, and I'd given you a couple definitions of work. Let me get my monitor focus a little there. I think that's pretty good. The initial formula that we used for work, we motivated from just reason, and we found that it's force dotted with the distance of travel. And that dot was nice because by doing force dot D, that gave us either the force component that was parallel to D, or it gave us the D component that was parallel to the force, so that you weren't counting the part of the force that was being wasted. But the problem with this formula is it only works if F is a constant. Over all of D. Now, in reality, if D's curving, as long as the dot product of F and D stays the same, in other words, the relative orientation of F and D are the same, then you could still use that formula, which that's kind of a weird thing, but that is a possibility. But generally speaking, if F has a chance of changing along D at all, you have to use a more robust formula. And that more robust formula, I believe I mentioned, was the integral of F dot DL. Okay. And this is technically something called a line integral. And Cadmium, I apologize again. This is another chance where not only am I going to have to teach you something that you haven't covered in your calculus class, most calculus classes never get to this. So this is really a third semester advanced calculus problem. So in other words, if you're lucky enough to go to a really a school where people test in with a lot of courses under their belt already, then you might get in the third semester to the line integral. But usually people don't see it until they take advanced calculus. So I apologize, but yeah, we're going to teach you something that you haven't yet learned in math. The good thing is this is one of the easier things. It has a dot product. So what you have to do is you have to express the force in terms of like I hat, J hat, and K hat. Those are the preferred ones, because if you do something other than I hat, J hat, or K hat, then you got to integrate those babies too. And then you got to break up the path along which you're pushing the thing or whatever. You got to break that up into infinitesimal segments and let this little DL vector sort of represent the tangent vectors for that little path at each little segment. So it can be quite complicated. Really what you're doing ultimately is, if you imagine just along one dimension, say X, then you can imagine the force actually varying at small x and then large X. So maybe at small x, it'd be a very, very small force, but then you get up to a bigger X, say right here, and it's a kind of big force, but it's nearly constant for a lot of different X's, right? You can see these are all really close to the same F value, but then it varies quite a bit to this X value and this X value and this X value. Ultimately, when you compute this thing, it turns out to be the area under the curve. Okay. But if you're actually looking at the path, what we're imagining is, say, this is the actual path that you're pushing the thing, not to be confused with this graph. It's just the same drawing because I'm horribly unimaginative. So what you'd imagine is breaking up this little path in this little segment. And right here, you'd say the tangent line for that would be DL. And maybe at this point, the force might be like this. And then you have to take the dot product right there. But then over here, the tangent vector might be this one, and the force might be this one. And that's really what you're computing is all those little parts. And it seems a lot more horrible than it is. So let me give you a good example. It turns out, did I give y'all Hooke's law last time? I can't recall. I didn't think I did. And I'm getting the response, so I'm assuming that I probably didn't. So Hooke's law, and this is the same Hooke I told you about that was one of Newton's arch enemies. So Hooke's law basically says that when you apply a force to something, let's say a beam or a piling on its ends like this, okay? This is the earth pushing up on the piling, and this is a weight pushing down on the piling. It turns out that if I apply this force to this piling is actually going to shrink a little bit. And what Hooke discovered was the amount that it shrinks is directly proportional to the force that's applied. So we write it like this: F equals some constant times X. And it works really well for everything. I mean, it turns out as long as you don't go too far. It also applies, by the way, when, let's say, the earth is holding the piling down, and this side I'm trying to pull it up because it's a piling that's holding up a house that's in the middle of a hurricane, right? So this force pulling on it will actually cause the piling to stretch a little bit. And as long as you don't go outside of its range of elasticity, then this is always going to be true. You've probably all seen like a slinky or something that's got one bad link in there. It's got several bad links. What's happened is someone stretched that one link or several links too far where they've gone beyond their range of elasticity. And this doesn't necessarily apply very well anymore. So that's the case. Now, it turns out with metals and wood and stuff like that, that stretch or compression is itty bitty except for the hugest of forces. And I'm not sure hugest is a word, but anyways. So you have to, do stuff like look at a vertical piling on a 100-story building after it's been loaded with weight before you could see even a millimeter of shrinking, right? So what we do to study it is we use like a spring instead, and in that case it's really obvious because the metal, by making it into a coil, it automatically compresses quite a bit, but it still obeys Hooke's law, where the force is proportional to the X. But when they do it for a spring, they say the force that the spring applies, F spring, is equal to negative Kx. And the reason why they do that is you can imagine if this is a y-axis and this is the x-axis, then if I apply a force pulling this box way out here, so the box is moved from here to here, the spring, on the other hand, has stretched all the way like that. Then what I see is my X went this way, but the force the spring is applying is this way. So that's why that negative's there. Does that make sense to everyone? So we tend to do Hooke's law with a spring just because it's easier to measure the stretch. So let's calculate the work required to stretch the spring from X equals 0 to, let's say, X1. So work is equal to the integral of F dot dl. This is where I'm going to do that actual line integral. Okay. So in order for me to stretch it, I'm going to have to pull it to the right. And I don't have to put a positive in there, even though a positive is automatically there, because the X being positive tells me the force is going to be in the positive direction. So I put an integral here and I say F is just going to be, in order for me to budget at all, I have to match the magnitude of the spring's force. So it has to be equal in magnitude of that as a bare minimum. So I'm going to say K times X, and then say the force is pointing in the positive X direction by putting an I hat there. Okay. So that's my force. And then I have to write my DL, which is a differential bit of the path. Well, here's the problem with a line integral. You've actually got to augment the argument, this part right here of the integral, or the ranges of integration, are both in some sense, to make it clear what path you're following and in which direction you're going. Okay, that's the difference between a regular integral and a line integral, is the argument and or the range of integration has to indicate the path you followed as well as the direction you went. But the rule is, when you're trying to indicate the path that's followed, you're just doing this. You're taking this and you're saying, like in this case, I might say dx I hat. Okay, that means I'm going along the x-axis, and the direction obviously is I hat. If I choose to let the DL dictate which direction I'm going, then I make sure this has the appropriate sign for the direction I'm going. I'm going to the right. This has a positive sign. So that specifies not only what path I'm following, I'm following the path along the x-axis, and I'm taking small intervals of dx, and I'm going in the positive direction. Well, now that I've chosen that, my job is to just put the range of integration from small variable to high variable. Okay, so I'm going to say from x equals 0 to x1. Now that happens to be the exact same way I'm going, but that's okay. But that's the rule. You've got to either choose this direction, choose this to show the direction, or choose this to show the direction. And whatever you do to the other one just has to be in increasing coordinate direction. So I will say chose DL to indicate direction. So range of integration had to be in an increasing coordinate direction. Okay, so that's the rule. You use one or the other to tell you which direction you're going. And then the other one automatically has to become the positive coordinate direction, or the increasing coordinate direction. Now that I've done that, I can go ahead and finish the integral. We'll note that the dot product is, as I've told you before, it's a linear operator. So I'm going to take another step and write 0 to x1, and I'm going to write kx dx I hat dot I hat. That's what I mean by it's linear. I can just pull all the linear crap in front of it out in front of both of the vectors. And now I know from last time that I hat dot I hat is in fact just 1. With that, I can now integrate. The integral of kx dx is just 1/2 kx squared. And now I got to evaluate it from 0 to x1, which I think you can all see is just 1/2 kx1 squared. So the work done in stretching a spring is just 1/2 kx squared to any distance x. That is an equation that your book has, as I was telling, I think it was Cadmium earlier. This is an equation that your book has, and it's equation. Well, actually, they didn't label this one, but I'm going to tell you, you can. Oh, yeah. No, they didn't tell you. Yeah, they didn't label this one. There's no 7-9 next to it, but I see it as the last equation on page 170. So I'm going to tell you, you can have this on your equation sheet. Okay. So that is, oh, sorry. So that is a formula you can use. And it just means that when you stretch a spring by a distance x, the work done in stretching that spring is 1/2 the spring constant times x. Now, the spring constant is something that has units of newtons per meter, as you can tell from Hooke's law. If this is newtons and this is meters, and clearly this has to be newtons per meter. So that's what the spring constant is. And it's a characteristic of the spring, provided the spring hasn't been stretched too far. Now, let me just to make it more clear about how we're doing this integral. It seems like from this one that there's no way you can ever screw up a line integral, right? Because I chose the direction, but this happened to go in the same direction. So what I'm going to do now is show you another one where this time I'm going to take and draw a little wall. And I'm going to draw my X, Y axes. Here's my X axis and here's my Y axis. I'm going to put my box right here. I'm going to put my spring right here. And now I'm going to apply a force that's actually going to act in the negative direction. I'm going to apply the force that way until the box moves to this position X2. So in this case, the spring's really wound tight like that. Okay. So if I want to calculate this work, I'm going to say work is equal to the integral of F dot DL. That's our formula, which is a formula you can use, by the way, just like these are ones you can use. They should be labeled, but if they're not labeled, I'm telling you, you can use them anyways. So I'll go ahead and mark those off. So you're allowed to use them whether the book's labeled them or not, but I do think the book labeled these. Anyways, the force is going to be, again, I have to give a force at least as large as the Hooke's law spring force is going to be. So when I'm pushing this way, the spring is going to push back that way. So I have to have at least as large a force. So that force is going to be K times X in magnitude. And notice as I'm going from X equals 0 to negative X's, it's automatically going to indicate that I'm going to the left, that the force is actually applied to the left. So I don't have to put a negative there. In fact, if I put a negative there, that would make this force point in the positive direction, which is actually the force that the spring is applying, not the force I'm applying. So there's my F, and now dot DL. So last time I chose to use the DL to indicate direction. I'll do that again. So in this case, I'm going to choose the DL to indicate my direction. So I'm going to say that the DL is negative DX I hat. The DX doesn't have a sign associated with it. It's just, a difference in X's. So this negative indicates that we're doing an integral from right to left. Now, the rule is, since I've chosen that to indicate my direction, I have to go in the order of increasing coordinate for my range of integration. Well, that means I have to go from, let's say, negative X2 to 0, which is exactly the opposite of the direction I'm going, right? So here's a case where you can actually see, oh, okay, so yeah, sometimes I have to do something weird over here. I always got to go in the positive coordinate direction for the thing that's not indicating my direction, okay? So this can all come out in front, and I'll get a negative K in front of the integral. I'm going to integrate from negative X2 to 0 of Kx dx times I hat dot I hat, which we already know is 1, right? So this is going to be negative 1/2 Kx squared from negative X2 to 0. So with this one, we can see that when X is 0, I'm going to get negative 1/2 K times 0 squared minus negative X2 squared. The minus on the X2 doesn't bother anything because that's squared, but luckily it's the second part of the integration. So that becomes a negative, which cancels out that negative, which gives me 1/2 Kx2 squared. And that's correct, because notice I pushed to the left and the object moved to the left. So that should be a positive work. When you push in the same direction that the object goes, or at least a component of your force points in the same direction as the object goes, you should get a positive work. Otherwise, the thing is doing work on you, okay? Now, what if I would have done this integral instead by letting the range of integration dictate it. Well, in that case, we get W equals the integral F dot dl, which in this case, I'm going to say, all right, this is going from 0 to negative x2. There's my direction. I've indicated my direction, right? My force has to be K times X I hat. And now I have to just dot it with DL pointing in the positive coordinate direction. So that's going to be DX I hat. So this is the positive coordinate direction because I chose my direction by these two things. Well, this just becomes K times the integral of X dx from 0 to negative x2. And now that's going to be 1/2 kx squared from 0 to negative x2, which is going to give you 1/2 k times negative x2 squared minus 0 squared, which again gives me 1/2 kx2 squared. Okay, so that's the two ways you can choose to do your line integral. And if you take the second semester course, you're going to be doing not only line integrals, you'll be doing surface integrals. And you'll do surface integrals with dot products in them and surface integrals with cross products in them and all sorts of crazy stuff. So just be prepared. We're going to teach you a lot of math. Well, I got one last thing. I've only got like 3 minutes left. This is handling the work, but now let me take and use Newton's second law and give you another theorem, or what we call the work energy theorem, or the work energy law. What we're going to do is we're going to say, well, I know that the summation of the forces, which is really the net force, net force, is equal to mass times acceleration, which we could also write as F net is equal to m dv dt, right? So if I want to calculate the net work, then I want to take all the forces F net and dot them with their DLs. So I'm going to say F net dotted with DL. And now I'm going to integrate that. But the other side of this would be equal to the integral of m dv dt dl, right? Because this F net really, if I put it in vector form, it's got to be like that. So I can either put that there or the DL, either one doesn't really matter. So when I do this, I really get what the total work done is. But on this side, I can write this as the integral of m dl dt times dv. Now I can say, for instance, the DL and the dv could be dot product. That's a nice way of saying it, because I did dot product to begin with. So I'm doing this and this, but dl dt, notice that's the differential path or distance divided by dt. So that's really a velocity. So I end up getting integral of m v dv, because v dot dv is just v dv. Now if I integrate that, I get 1/2 mv squared from v0 to v final. Okay, that's been this range of integration the whole time. So what I found is that the net work done on any object is equal to 1/2 mv squared minus 1/2 mv0 squared, which we define kinetic energy equals K. Some books use T, by the way, is 1/2 mv squared. Then we see the net work. If you add up all the work done by every force acting on an object, that's what W net is. If you add all those up, that's going to be equal to the change in kinetic energy. And that's called the work energy theorem. It's very powerful. For instance, we can use it to determine the speed of a driver by his skid marks that they left just before a collision. So that's one of the typical things. But I now have given it to you so you know basically what it is. I haven't given you an example though yet And that's really the last part of this chapter. So we'll work a couple examples next time, but we're actually done. Time is up and you guys are free to go. I've already opened up the lab for this week. You can go, I would suggest you watch the video of how the data is taken before you even come to the lab. And then you can just get started doing the lab as soon as I get you in your breakout rooms, and you'll be able to be done quicker. So if those of you have lab today, that's already available. Those of you have lab tomorrow or the next day, I will have those available in a few as well. I did fix the test 3, by the way, so that should be working now. Anything else anybody have? Thanks for coming, everybody.
I had a question concerning one of the questions for the homework. It
Go for
it has to do with gravitational attraction between a hollow sphere and an object inside it.
Yeah.
The homework states that there's no gravitic interaction between the two objects if an object is inside the hollow sphere. But
Right.
I was under the impression that the hollow sphere would have, like, it has an overall it still has an overall center of mass at the center of the hollow sphere.
Right.
So just as an example, give you like the example of a Dyson sphere around a star. You have a Dyson sphere of theoretically perfect mass distribution.
Mhm.
So the center of mass of the Dyson sphere would naturally be attracted to the center of mass of the sun that it is around.
Exactly.
And so it would be like gravitationally stable. But there was a question on the homework that was saying that that was not the case.
Right.
Like if something were to strike the Dyson sphere and impart any amount of kinetic energy on it, that the sphere around the star, it would just drift until it touched the star.
Right.
I was under the impression that it would just kind of be, I don't know, stable for some reason.
Right. Well, think about it this way. Let's say the sun is this little dot, and that's the center of also the Dyson sphere. And let's say the Dyson sphere is really huge.
Yeah, it's got to be large.
Okay. And then we'll say it's even chunky. So they've got some stuff here. Maybe they built some office buildings or something, right? Well, what you do is you could say, all right, well, let's think about the gravitational force of this part on the sun. Well, clearly that part on the sun is pulling the sun towards it.
Okay.
But what about this part diametrically opposed to that part? Well, that part is pulling on the sun exactly an equal amount, but in the opposite direction.
Yeah.
So, and that's true for every point along here. So what you see is there's no net force on the sun due to this thing. Now, when that shifted so that the Dyson sphere maybe is off center, like this, that no longer holds because this point is a lot closer to the sun. So the force is a lot bigger on this side than it is than it is on this side. So it's going to be an unstable equilibrium. There is some range where it's probably, if you wiggle it a little bit, it's probably got some stability. But once you, I would guess, once you go a little bit further than just a little bit, there's probably going to be some point where this is going to overwhelm the force of attraction on this side, and it's going to suck it right in until it hits the star. But the main reason why you're not going to feel any force inside is because of the symmetry of the situation, where basically every bit of mass, if this is really a smoothly distributed mass distribution, then every bit of mass on this side will cancel out every bit of gravity due to the mass on this side will cancel out every bit of gravity due to the mass on this side. Does that make sense?
So that would be why the here. Yeah, it says that the net force that the sun exerts on a Dyson sphere, basically while it is within the Dyson sphere, is always zero.
Right.
I don't know, because like you did say that bit where when the sun is closer to one of the walls, it would seem that it would attract. it would attract the closer wall more.
It does, yeah, absolutely. In this scenario, when it's off center, then yeah, that's why I'm arguing it's not really a stable equilibrium, because a stable equilibrium means that if you give it a little push out of equilibrium, the forces tend to restore it. This is an unstable equilibrium, meaning as you give it a little push, the forces tend to make it get worse. So just pushing it a little bit this way, so I was actually wrong in my initial conclusion, just pushing it a little bit this way means this part has a lot more force than this part, or excuse me, than this part. So it's going to continue to make it get closer and closer and closer. So it's really an unstable equilibrium.
So, well, and so, all right, let me read out the question. It just says, what is the net force that the sun would exert on a Dyson sphere were it to get displaced off center by some small amount? And the answer is still 0. But wouldn't that essentially not be true, since it is exerting a force on the Dyson sphere, since it will tend to accelerate towards the closest wall of the sphere?
Yeah, that's what I was thinking. So you said it's the force of attraction, if it was displaced a little bit from the center, would be 0.
Yeah, the answer on the correct answer on the homework says 0. It says there is no net attraction between a hollow sphere and a body inside. That is part of the explanation of the answer.
Yeah, I need to think about that a little bit. Now, I remember in the Principia Newton did some kind of discussion about this. So I probably need to refresh myself on this, but right now I'm leaning towards the BS.
I mean, maybe
because,
just for the purposes of the calculation that it's a small force. Well, I mean, then again, like it's a sun and a Dyson sphere. That's massive amounts of, I guess mass, for lack of a better term.
right.
There should be some force between the two.
Yeah, what I'm thinking of though, and this is probably where they're leaning, is next semester we'll learn basically something that's equivalent to gravitational law. We'll learn Coulomb's law, and then Coulomb's law can be derived from something called Gauss's law. And when you do that, you can see that basically when you put something inside of a hollow sphere, in that case it'd be charged as opposed to massive, the force on it is 0. And it doesn't, I seem to recall, it doesn't have to be from symmetry. That's why I'm thinking that maybe it's not BS. I just haven't worked out the details to show it myself. In other words, for this, what we'd say is there's a gravitational field G, and this is not 9.8 meters per second. It's a gravitational field, but it sort of looks just like it. Namely, it would be G times the mass part of the Earth. So I'll put a prime on that, just because if you're not as far out as the edge of the Earth, if this ball were the Earth, for instance, if you're not as far out as the edge of the Earth, then I have to take the fraction of the mass that's inside the circle whose radius you're on, I should say. And then R, again, I'll put a prime on that, squared. Okay. Well, the law that's the equivalent of gravity is that the closed integral of G dot dA is equal to basically the mass enclosed inside of a sphere that you make over some number. Okay. And this allows you to actually calculate how much force of gravity it is. And it turns out when this law is worked out, and this is a surface integral that I was telling you about earlier, so don't get too caught up in the math because you can't do it yet. But there's a way where we do this with electricity and magnetism that basically shows if the net mass inside a particular sphere is 0, then there's no force on it. So if you took a sphere this large, where it just hits that, there's no mass inside of it except for the one attracting thing. So the net force there would be 0. And that's what's making me think that they're making that conclusion. I just never put that together myself. So it's probably something that I should have known, but did not. So I will try to see what I can find out about that and let you know either via email, or I'll make a video, or I'll tell you guys in class next time.
Okay.
Okay.
All right. Thank you.
Yeah, it seems counterintuitive to me, but I'm thinking it's because I haven't gone back and looked at gravity in a classical way, because I studied my study area was general relativity, so that's a non-classical way, but it probably has an equivalent in that too. So it's just something I missed. It's a hole in my knowledge that I got to check on. Okay.
Okay. Thanks.
All right. Sorry, I couldn't help you better.
Yeah, no problem. I mean, I got I got that answer. I forget where I got that from. I think
Jag might have had it.
Let's see.
And I don't recall reading it in the book, but
So
there might be
so
something.
yeah, no, it's in the hint for the problem. It says basically says the sun is modeled as a spherical body with mass centered, concentrated at the center. The Dyson sphere can be considered the same, with a mass located at the center of the sun because the sphere is around the sun itself. And then
Right.
it says to find the force, recall that no work is done on a point mass that moves inside a spherical shell. And I was like, that seems
yeah.
a little strange, but it said no work is done, so I was like, okay, 0 newtons.
Yeah, that's exactly
yeah,
that's
it's
exactly
still-
the description that we're getting here too, because this turns out to be exactly equivalent to that statement you just made. We'll learn that in the second semester of the course, but yeah, that must be it. So yeah, I'm going to go with it and say yeah, that's absolutely right, and it's just something I hadn't developed in my own brain.
Gotcha.
That's sad, but it's cool that I'm learning something at 51 years of age.
Yeah, there you go.
All right,
All right,
thanks,
thank you.
Gavin. Sorry about that. Brandon, Marcus, anybody have any questions? Joshua, Jacob?
No, I'm good.
All right, well,
I'll go last.
Oh, yeah, go ahead.
Oh, I was just gonna wait till everybody else. does.
Okay, gotcha. I don't look like anybody has any questions, so if you have one, go ahead and give it to me now, or I'm gonna go ahead and log out. If you have a question you need to ask in private, I can go to a breakout room and I can stop recording as well. So if you need that, just let me know. You can chat it and tell me or whatever. All right, see you everybody. Bye-bye. If you have lab, I'll see you soon.